All right, so we're going to pick up on page 12 of our momentum booklet. And we're going to start doing these vector diagrams, specifically momentum vectors, that are going to show the mass and the velocity. Earlier we did some velocity vectors, and those were just simple arrows. But now we have to include in our vector diagram something to represent the mass. So it's one step more complicated than a velocity vector. So we're going to do some math over here, and then we're going to do a vector diagram over here. The first problems give you a head start. Eventually, you're going to have to do this whole thing on your own. So, question 1A. A car of mass 2,000 kilograms is traveling at a velocity of 10 meters per second. Calculate the momentum. So we just have to fill in these to begin with, and like I said, it's giving you a head start in the first couple of problems. So mass, well, it gave it to us right there, 2,000 kilograms. We just bring it down. Velocity, 10 meters per second. Let me see. I'm going to call on David. Tell me what the momentum is, David. What is P? David, are you there? Maybe you're writing me a note. Well, somebody else has arrived. Gus got here. Woohoo! Hey, David, if you're there, please tell me what is P? What is the momentum?
I'm not sure.
Oh, well, let's look at the equation. Here's the equation, right? P equals mv. Yeah? Well, I want P. All you have to do is multiply.
Would it be 20? Yeah, 20,000.
Exactly. Perfect. For some reason, there we go. 20,000. So an easy way to do this in your head is you just go, whoa, anytime you multiply by 10, you just throw an extra zero on there, right? So it's 20,000 kilogram meters per second, which is a weird unit, but that's how we measure momentum. 20,000 kilogram meters per second. Now, next, draw the momentum vector diagram. Trace the image to practice drawing it. So for the first couple, they've given it for you. So I'm going to start by making a circle. This is representing the car, and they are showing the circle of this size. So go ahead and draw over it. You could also use the pencil. Then we want to show an arrow because the car is moving in this direction at 10 meters per second. So we're going to put an arrow in that vector diagram. Okay, so they point out that the grid is there because the vector needs to be drawn to scale. That means if your momentum doubles, the length of your momentum vector doubles. If you have more momentum, you need to make a bigger arrow. Lastly, we need to outline the boundary of the system. So we're not going to study anything outside of this boundary. We're only going to look at this zone as we're studying the different influences on the car and how it influences things around it. All right. So hopefully that's pretty straightforward. I think that we could have even shrunk this boundary down a little bit to be just around the ball and where the momentum is moving it during that time. Okay, next problem, 1B. If the mass of the car doubled, what would be the momentum of the car? How about Josh? What's our mass going to be? If the mass doubled, well, we have to refer back to the first problem to do that, I think, huh? Of course, I picked the one person that's not there anymore. That always happens. Okay, Quetzali.
Yes.
What is the mass of the car now?
4,000.
Yeah, perfect. It's going to be 4,000 because it doubled. We go back to what we started with. We double that. We get 4,000, right? Alejandro, what is our new momentum? How many kilogram meters per second are we going now?
Of 40,000.
Perfect. 40,000 kilogram meters per second. Just multiply, right? Whatever m is, whatever v is, multiply. You get your momentum. Now we're going to draw the momentum vector, and you can see, first of all, this was a bigger car, wasn't it? So notice that this circle is bigger than the first one, right? It'd be nice if we could make it exactly twice as big, although I think that's kind of hard to do with a circle. Maybe we should have made these as squares. Like if we'd done this for the first one, here's the first car. I think it's easy to tell that a square this size, oops, I'm having a hard time drawing it. A square this size would be exactly twice as big, right? So that'd be really nice if we could do them to scale, but they showed circles. You actually have your choice. I noticed that some of you have made some very nice cars in other assignments, so that's good too. Just make sure it's obvious which one is bigger and which one is smaller. So this is not exactly twice as big as this, but it's obviously bigger, right? Now it's much easier to draw an arrow that's exactly twice as big. So if it has more momentum, which it does, 40,000 compared to 20,000, then we should have a bigger arrow, a bigger vector. As a result, the boundary of our system is also bigger because it's a bigger object, a bigger car in this case, and it's going to move further. It has a greater momentum. We need to make the boundary big enough to enclose that thing. Okay, that takes care of 1B. 1C. If the velocity of the car from part A doubled, so we're going to go back to part A, we're going to double its velocity. If the velocity of the car from part A doubled, what would happen to the momentum of the car compared to the original momentum? Remember to go back to using the original mass. We're only going to change the velocity now. So let's see. How about Gus, will you give me the mass of the car here?
Yeah.
Okay.
Would it be 2,000?
Yeah, because we're going back to the original mass. Good job. Yep, that was a little detail that's not hard, but you do have to pay attention to it. So
Yeah.
good job. Vanessa, what about velocity now? See, the velocity from part A doubled. Here's part A.
So it would be this 20.
That's correct. It's now 20 meters per second. Perfect. Let's see. Sam, what do we have for the momentum now? Oh, and Kaylee's joined us. Yay. Looks like Sam might not be here, huh? Write me a note if you're here, Sam. Okay, let's see. I'm going to ask Kaylee then to calculate our momentum. What do we got to fill in down here? P equals mv. So what's our momentum? You have it, Kaylee?
P, no, I don't have it. Sorry, I just got here.
Okay, all we have, well, I just want you to do it now. We're all doing this together. So all you have to do to find momentum is multiply mass times velocity. Remember, here it is, P equals mv. So what?
20,000.
Try again.
What? Oh, 40,000.
There you go, 40,000. So notice that a shortcut for doing something like this, you just go 2 times 2, that's 4, and then count up how many zeros there are. In this case, there were 4 zeros, so we have to put those down. Okay, 40,000, but what? Oh, it's the same as this momentum, isn't it? But it only weighs half the mass. How can that be that it has the same momentum if it only has half of the mass? Oh, it's velocity made up for it, huh? It's going faster, so that means it's going to be harder to stop, even though it has a smaller mass. When I draw this momentum vector, I want to do 2 things that are matching the scale of these momentum vectors. First, I want to use a circle that represents the mass that I had earlier, right? I had a 2,000 kilogram mass, so I should use the circle that is also the 2,000 kilogram. So I'm just going to copy and paste this using Control C and Control V. Then I'm going to drag it down here, and I'm going to put it right there. Okay, so my momentum vector includes the mass, and I want it to be in line with these other masses. So I made sure I used the same circle. Next, I need to make a momentum vector arrow, and this one needs to represent the amount of momentum, this arrow, and since it's the same as this arrow, this momentum, I should just copy and paste this arrow. The same size. Even though it's a smaller mass, it has the same momentum because it has a higher velocity, and that made up for it. So I'm using the same vector arrow as this second problem, but I'm using the same mass circle as the first problem. Next, I need to add the boundary of the system, which I think should be the same size as this one. Since it had that same momentum, it's going to keep moving through a bigger space than this one did. And then you have a bonus question here. So you don't have to do that, but you can if you want some extra credit points. Okay, so we're moving on to 1D. Compare the length of the momentum vector from C to the lengths of the momentum vectors in diagrams of A and B. Summarize what you noticed by completing these sentences. So I think, will you guys check yours? I think I found on Friday that this word right here, on yours it might say mass. Is that true?
Yeah.
Okay, it changed yours to say velocity. This is, I corrected it. So yours should be, scratch out the word mass and change it to say velocity. Okay, because we didn't double the mass for part C, we doubled the velocity for part C. So when comparing the momentum vector from C to the momentum vector of A, I noticed the length of the momentum vector, in other words, the arrow, did what? Because the velocity doubled. What do you think? What are you going to fill in here? What happened to the length of that momentum vector? Comparing C to A. What happened to the length of the vector here? Please fill that in for yourself. Yeah, and specifically, ideally, if we did it perfectly, how much longer would it be? Look at the momentum number.
Double the size, right?
Yeah. So the diagram ideally shows that by having an arrow in C that's twice as long as the arrow in A. So go ahead and fill that out. Then, this one you've got to do more for yourself. When comparing the momentum vector from C, again C, but now we're going to compare it to B. So you need to finish this sentence in two ways. First, you have to say what happens. Let me see. So notice that first that you said what happened. And then you explained why. Here's the why. So you need to do both of those to finish this sentence. When comparing the momentum vector from C to the momentum vector of B, I noticed, how did these two compare? And then tell me why. And in this case, it's going to be a little more complex because there were two things that were different between B and C. Even though the momentum ended up the same, both the mass and the velocity were different. So you should include both of those in this sentence down here. So take a minute to finish that up. Okay, so let's read through this. You should probably highlight the important text as we go here. Direction matters. When vectors are added, it's important to pay attention to direction. If you've noticed, for the previous problem, plus was indicated in the grid to show that the positive direction of movement is to the right. Therefore, minus would mean it's moving to the left. Adding vectors is like adding numbers. If two positives are added, the result gets bigger. If a positive and a negative are added, the result is smaller. It's just like working with negative and positive numbers. You could also have two negatives, and then it would also get bigger, but in the negative direction. Either way, when momentum is conserved, the total always results in the same value. While we're talking about direction mattering, I do want to point out that moving up and moving down, these do count as directions. I scored some of your assignments that were practiced to get ready for the project here, and I noticed that some of you said it was a direction if it was saying left, right, or if it was saying north or south, but some of you didn't say it was a vector when it said it was moving uphill or going downhill. Those are directions. Or something like towards the goal is also a direction. So for the following problems, you'll be asked to draw the momentum vector diagrams. Please make sure you scale the vectors to each other. In other words, if the momentum of problem A is twice the momentum in problem C, the momentum vector in A should be twice as long. Use circles in your diagrams to represent the objects in motion. I don't really care if you use circles. So 2A, we have a football player. He's 100 kilograms. He's running at 5 meters per second. You're going to find his momentum and draw the diagram to represent his motion. Then you have a softball player, 75 kilograms, another softball player of 50 kilograms. So notice that they're all different masses, and so we should be able to see in your diagrams that they're different masses. They're also moving at different velocities. When you calculate their momentums, your arrows need to match their momentums. Okay? Now, I'm going to have you do this on your own in a minute. Not quite yet. Once you're done with this page, when we come back on Wednesday, we're going to start looking at collisions. We're going to look at momentum when things collide with one another. Not just a single moving object, but remember, it's about how difficult it is to stop that object is what we mean by momentum. So what happens if two things crash together? And isn't that exactly what happened with Newton's cradle? Is we crashed one ball into another or three balls into others, right? So that's going to be for Wednesday. So I want you to finish, looks like we're on page 13. I'm going to want you to finish that for yourself. But also today, I want you to do one other set of practice problems. And it looks like this. Somebody let me know, can you see this momentum vector practice?
Yeah, you can.
Okay. So it's basically just practicing some more of these problems. I'm going to zoom out. I think there's just, yeah, there's basically 5 of them because number 4 has 2 parts. And these ones, because they're very different problems from one another, you don't have to draw the momentum vectors to scale. And you just won't have room because this one's a car traveling at 27 meters per second, but this one's the SpaceX Falcon 9 rocket traveling at 17,000 miles per hour. And it has a huge mass. So that's why this one's tilted sideways to show it launching upward. And so this is not going to be to scale to this problem. Here's a much smaller object, a bowling ball. Okay, and an even smaller object, a bullet. So you're going to find the momentum of the bullet twice. Once when it's just thrown, and then when it's shot at a target. Okay? And then you're going to draw those 2 momentums vector diagrams. Now these 2, since it's the same object, you should have the same size, at least for the same mass. It should be to scale for these 2. These other ones don't need to be to scale. On this page, back in the project, since they're all people, they're relatively easy to compare their sizes. These ones do need to be drawn to scale. So, is there anybody that doesn't know what I'm talking about when I say they need to be drawn to scale or they don't need to be drawn to scale? Okay, so basically if one is twice as big as the other, then the circle that represents it should be twice as big. If it has half the momentum, then the arrow should be half as long, right? So this class actually continues until 10:10 for another hour, huh? So that's the amount of time you're expected to put in. And I don't even think it's going to take you that long. And if you're caught up with all your other work, great, then I don't mind. You're free to do whatever you need to do or want to do. But if you're behind on your work, you need to put some more time into this class, right? So you have an hour to work on whatever assignments you need to finish. And that includes momentum vector practice that I just showed you with the rocket and so on. That one is due on Wednesday, so that one needs to get done today. And then you should also finish, what did I say, page 13 needs to be done on the project. Yeah, you need to finish page 13 on the project by yourself and the momentum vector practice by yourself, all right?